In this problem, we've been told to find the area of the shaded region, and the shaded region is here. So thinking about that shaded region, if I draw in my arbitrary cross-section, so I've got this vertical rectangle, and I know I'm trying to find the area of it. Well, the area of a rectangle is the height times the base. For my teeny tiny skinny rectangle here, my base is a little bit of dx. And I'm going to get my height by thinking about the top height minus the bottom height. So that top height is the square root of x plus 2. The bottom height is 1 over x plus 1. And then we're going to add those up calculus style, meaning we're going to write an integral. In terms of our limits of integration, these rectangles would come as far to the left as x equals 0 and as far to the right as x equals 2. This question asked us to finish off this integral. What Dr. Dedell has been saying in class is that on the exam, and this is pretty consistent, he usually asks you to set up area problems like this, not to finish them off. But I think it's good practice to practice our integration techniques. So let's go ahead and finish this one off. Looking at this, I'm actually going to treat this as if it were two separate integrals, because these two functions aren't similar enough for me to try to find one antiderivative. I would actually break this apart to go 0 to 2, x plus 2 raised to the 1/2 power, minus the integral from 0 to 2 of 1 over x plus 1 dx. This part, I'm thinking about a u substitution. That x plus 2, if that were equal to u, then dx would be my du. This is the kind of u substitution that I tend to not even write out after I've had a lot of practice with u substitutions. This would become u to the 1/2, and this would be our du. If we're writing this as a u substitution, we need to be sure to switch the bounds for integration. So I started off saying I wasn't going to write out the u substitution. I think I need to so that I can swap the bounds. On this one, I'm going to come off to the side, and hopefully we can read my red marker. If u is equal to x plus 2, then when x is 0, u would be 2. And when x is 2, u would be 4. And I'm getting those by plugging the 0 in for x, or plugging the 2 in for x. Now, when we rewrite this in terms of u, this becomes the integral from 2 to 4 of u to the 1/2 du. Evaluating that integral, I'm going to add 1 to the exponent, divide by the new exponent. I would end up with u to the 3/2 divided by 3/2, and we would be going from 2 to 4. Dividing by 3/2 is the same thing as multiplying by 2/3, and I'd end up with 2/3 of 4 to the 3/2 power minus 2/3 of 2 to the 3/2 power. And although I could simplify the 4 to the 3/2 power, I won't be able to simplify the 2 to the 3/2 power, so for now I'm just going to leave that alone. We still have to address this other integral. Here, I would also do a u substitution, or just go directly into what the answer is. Because this is one of the forms for our simple antiderivatives from chapter 4, I would take this straight to natural log absolute value x plus 1, evaluated from 0 to 2. That's going to leave me with I'll jump straight down here to the bottom line. That's going to leave me with minus, we'd have ln, absolute value of 3, minus natural log, absolute value of 1. And if we simplified that, we get something, but I don't even think we need to simplify it. I think we can stop there. One thing that we might notice is that natural log of 1 is equal to 0. So we don't really need to, if I were going to simplify anything, I'd probably get rid of that piece.